procedures and methods for calculating duct resistance will be described based on calculation examples. Samples will be used for explanation, so download the relevant data from the specified website and keep it close at hand. Some key points when selecting fans will also be described. Introduction. Calculation of duct resistance is carried out to determine the level of resistance in the planned duct system and the required performance for the fan. Resistances are subdivided as follows. 1. Frictional resistance of a straight duct. 2. Local resistance. 3. Resistance of machinery. Frictional resistance of a straight duct, designated item 1, is calculated usually by multiplying the unit frictional resistance by the length of the duct. The unit frictional resistance is determined based on a duct measure or a diagram, or such. Local resistance, designated as item 2, is generated at deformed portions where ducts are bent, branched, joined, and transformed, or dampers. A table of the resistance coefficient for elbows. A table of the coefficient of resistance for extended ducts. A table of the coefficient of resistance for narrow ducts. A table of the coefficient of resistance for combined ducts. A table of the coefficient of resistance for branched ducts. If you cannot find the required coefficient, adopt it from various literature or manufacturer's data. In addition, the conditions to be followed for resistance calculation are specified in such engineering materials. Be sure to calculate based on those conditions. In particular, note that the wind velocity changes at a branched or combined point when you use such conditions. Determine the resistance of machinery, designated item 3, such as by viewing technical data about coils and filters, and such, issued by manufacturers. Resistance of machinery such as air conditioners is referred to as internal resistance. Internal resistance causes pressure loss in system elements including coils, humidifiers, and filters. Initial pressure loss and final pressure loss are significant for filters. Initial pressure loss is referred to as loss received by a filter when it is used for the first time, while final pressure loss is referred to as loss which indicates that the filter should be replaced. In general, approximately twice the initial pressure loss is equal to the final pressure loss. Let's use the air conditioner system shown on the slide as a sample to calculate duct resistance. We are going to calculate the duct resistance of the inlet port most distant from the air conditioner, then that of the outlet port most distant from the air conditioner. In this sample, the duct resistance of the inlet port is calculated first. If the fresh air intake exists at the end of the line extending to a point most distant from the air conditioner, first calculate the duct resistance of the intake. Consider a series of ducts with the same duct size through which air flows at the same flow rate to be one particular section. Use that section for calculation. First, let's begin calculation of the duct resistance on the inlet port side. Designate the starting point as A, and consider the portion from point A to the point where the airflow rate changes to be one section. Here, assume the inlet of the air conditioner to be point B. The portion from the outlet of the air conditioner to the chamber is designated as Z. The portion from the chamber to the first branched point is designated as D. The intermediate branched point is designated as E. The last branched point is designated as F. The outlet is designated as G. The duct resistance of the section from points A and B is as shown on the slide. Use the calculated wind velocity to calculate the dynamic pressure. Determine the resistance coefficient of the inlet port with reference to engineering data provided by manufacturers. In the sample system, a slit is adopted. The resistance coefficient is 2.3. Calculate the actual wind velocity based on the inlet port size and the aperture ratio. Check the table to confirm the resistance coefficient of the wind velocity to be used for calculation. The face velocity may sometimes be used. The pressure loss is determined by multiplying the local resistance coefficient by the dynamic pressure. Now, how to determine the resistance of a drastically narrow duct is explained. Please be careful to choose the correct wind velocity to be used. Wind velocities shown on the table are those which are obtained on the outlet side of the duct, which is the side where the duct is fully narrowed. The area of the cross-section of the duct on the inlet side is 0.66 square meters, while that on the outlet side 0.2 square meters. The area ratio of them, therefore, is 3.3. If the resistance coefficient is obtained as an intermediate value, you can use the maximum value within the target range or interpolate it to determine the resistance coefficient within the target range. Here, the resistance coefficient is calculated using the maximum value within the target range. Assume that the extended angle is 180 degrees. The area ratio is 3.3, or between 2 and 4. The resistance coefficient to be adopted is 0.41, which is the maximum value among those for the corresponding area ratio. Multiply the local resistance coefficient by the dynamic pressure. Multiply the unit frictional resistance by the duct length to calculate the resistance of a straight duct. Use calibration scales such as duct measures to determine the unit frictional resistance. Determine the resistance coefficient of the elbow based on the width, height, and radius of its curvature. Determine the width and the height in accordance with the duct plan. Here, consider the first rising elbow whose width is 400 millimeters. The height of the elbow is 500 millimeters. The ratio of the height to the width is 1.25. The ratio of the radius r to the width w, or d, is 1, where the track depicting the central axis of the elbow is an arc of the circle whose radius is represented by r, while the width w, or d, is that of the elbow in the radial direction of the circle. The resistance coefficient is 0.21. The second elbow is bent laterally. Its width is 500 millimeters. The height is 400 millimeters. The ratio of the height to the width is 0.8. As a result, the resistance coefficient is 0.23. Resistance of an elbow depends on its width, even if its duct size is the same. The wider the elbow is, the higher the resistance is. Note that resistance depends on the direction elbows are bent, as shown on this slide. The position of the guide vane to control biased flow should be as shown on this slide. Different resistance is caused depending on the shape of the duct. Therefore, keep the optimal duct plan in mind. Use the resistance coefficient obtained when the damper is fully opened. The resistance coefficient of an extended duct is determined based on the ratio of the inlet area to the outlet area and the extended angle. Here, the duct inlet area is 0.2 square meters, and the duct outlet area is 1.8 square meters. The area ratio, therefore, is 9. If the extended angle is 180 degrees, the resistance coefficient is 0.88. Calculate the dynamic pressure based on the wind velocity on the inlet side. This is the end of resistance calculation of the section between points A and B. In the same way, calculate the duct resistance of each section. Now, resistance calculation of the section from point B through point C is described. You can calculate it in the same way as done for the section between points A and B. This section consists of 3 types of ducts: the extended duct at the fan discharge point, the straight duct, and the drastically extended duct. Set the extended angle at the fan discharge port at 15 degrees. Set it within 30 degrees at most. Here, the extended angle is 15 degrees. The resistance coefficient is 0.33 from the ratio of the inlet area to the outlet area. Now, resistance calculation of the section from point C through point D is described. Each resistance of the drastically narrow duct, the duct, and the VD can be determined as described above. Calculate the value X for the branched side of branched portion. The resistance coefficient is 0.4 because the calculated value X is 0.8. Don't for ducts instructs that chambers should not be used without careful consideration because they generate high resistance. Please consider using an elbow or other appropriate materials for construction. Even if chambers are used, take proper measures including using the duct plan to adequately reduce the wind velocity. To determine the resistance of the section between point D and point E, the resistance of the branched point and that of the straight duct are calculated. The resistance coefficient of the straight side of the branched point is different from that of the branched side. In this case, the resistance coefficient of the straight side is used, so see the main duct. Calculate the wind velocity ratio of the non-branched side to the branched side to determine the resistance coefficient. In this example, the wind velocity of the non-branched side is 6 meters per second, and that of the branched side is 5.3 meters per second. The wind velocity ration is therefore approximately 0.88. The size of the branched side is narrowed. How to determine the duct resistance is already described above. Determine the resistance coefficient in the duct plan. Hereunder, duct resistance of a number of branched sections and narrowed sections are summarized. When you calculate duct resistance, you should calculate it on a section basis. Data to calculate duct resistance of the sections between points E and S and between points F and G are shown on this slide. In the same way as previously described, carefully consider individual dimensions to determine the resistance coefficient. Determine the resistance of the outlet by referring to engineering data provided by manufacturers. Determine the total pressure of the fan by adding up all resistance values. Determine the discharge dynamic pressure of the fan to calculate the fan static pressure. Expect the allowance coefficient to be 10% or so. Here, calculation is carried out by setting the allowance coefficient at 10%. Based on the required static pressure of the fan as shown on the slide, select a fan based on reference data including performance curves. Note that the series of resistance calculations as described so far should be used under the condition where the airflow is relatively uniform. The duct resistance of actual ducts may not fall within the range of calculated values. In particular, significantly high resistance may be generated in the circuit of the fan where the wind velocity is high and the airflow is unstable. The pressure loss at joint portions of fans is referred to as system effect. That system effect will be briefly explained. First, let's think what will happen if the system effect is not estimated. In that case, the actual resistance is higher than the calculated resistance. Of course, the actual flow rate is below the set flow rate. To achieve the set flow rate, the resistance generated as a system effect must be added. If not, different fan performance will occur. The distribution of wind velocity is biased in the area where the air is just blown out from the fan. Some distance is required to achieve the almost uniform distribution of wind velocity. This distance is referred to as effective duct length. If there is an element or portion which reduces the airflow rate, including a curved portion, large resistance is generated. The effective duct length is calculated based on the discharge wind velocity of the fan and its duct size. Now, how to calculate the system effect is explained based on a sample. We use conditions shown on the slide. By the way, the term elbow shape means a curved shape as shown on the slide. In this example, we use an elbow placed in position C. Let's select a symbol from the selection table for the systematic effect diagram. Based on the conditions, the ratio of the effective duct length to the distance from the outlet of the fan to the elbow is 25%. See the area ratio of the discharge port to the outlet of the fan. This ratio is identical to the actual area ratio of the discharge port to the outlet port of the fan. Referential values are shown on this slide. Here, the ratio 0.7 is used. Select symbol S, because the position is C. Determine the system effect based on the diagram. Symbol S has been selected. See the line extending from point S. Based on the conditions, the average wind velocity is 15 meters per second. Determine the system effect from the intersection. It is 115 pascals. If the system effect is caused, overwhelmingly high resistance, which cannot be compared with any other resistance, is generated. You cannot offset it even if you calculate resistance as carefully in detail as possible. Your role is, therefore, to prevent such problems and plan optimal ducts. Finally, some key points for selecting a fan will be described. 1. Is there any problem based on the expected variation of fan performance along with the change of resistance? Understand fan performance curves. After predicting how the behavior of fans varies, select an appropriate fan. A different gradient of performance curve shows a different flow rate occurring with pressure variation. Fans with relatively gentle gradients are often selected for general air conditioning systems. The flow rate of the air passing through the variable air volume system changes even if resistance changes a little. Fans with sharp gradients are advantageous if flow rates, including circulatory flow rates in clean rooms and duct wind velocity and dust discharge flow rates, are not changed even if filters are closed. Two, never fail to confirm the conditions of the fluid to be used. Information, including the fluid to be used and the operating temperature range, is displayed. If a fan not meeting the intended use is selected, trouble including failures can occur. Be sure to confirm the conditions of the fluid to be used. For example, the change of performance curve follows the change of set air temperature as shown below. If the air temperature rises, the performance curve shifts downward. The air flow rate is the same. When air temperature drops, the curve shifts upward. If the fan is operated in the same duct system, the flow rate is constant, but pressure and power change. Three, is surging of no concern? If the horizontal line of the fan static pressure intersects with some points on the performance curve, the fan performance changes at operating points between such points on the curve. In this situation, the fan operation is unstable. Vibration and noise are generated. The fan may fail. Select a fan so that only one operating point can exist on the performance curve. In the case of other equipment such as smoke dischargers, different duct routes receive different resistance. Duct routes with high resistance can act as surging zones. Be careful when you establish a duct plan, calculate duct resistance, and select fans. In principle, Take a Shot does not select Sirocco fans for smoke dischargers. Select other fans such as limit load fans for smoke dischargers. 4. Does the noise fall within the tolerance limit? Should some measures be taken? If tolerance limits for noise are specified, silence measures are required. When you take measures for silence, you have to take partial measures including installation of silencers as well as comprehensive measures including a duct plan and fan selection. For example, Consider whether or not the cost of construction can be reduced if a larger sized fan is used to reduce the rotation speed. 5. If a fan with a large capacity is considered, place special emphasis on the fan efficiency. The shaft horsepower is proportional to the airflow rate and pressure, while inversely proportional to the efficiency. Especially if you consider a fan with a large capacity, it has a great effect on the duct system. A fan with more efficient operating points is required to be selected. This is the end of calculation examples of duct resistance and fans.